Okay, let's calculate Einstein calculation of solid states, chapter specific heat, Boltzmann, Einstein, and Debye. Okay, chapter 2. So here you can see in our introductory we have studied that for solids we have specific heat equals to 3 into R, which is the ideal gas constant known as law of D'Alembert. Okay, so specific heat, which is equals to the energy change in energy per unit time, or we can say that rate of change in energy. So this is exactly equals to the 3 ORR. Okay, you have studied already in statistical mechanics that how we can prove these terms. Okay, 1/2R, which is the energy for 1 degree freedom, 1 degree of freedom for per atom. Okay, so this is the kinetic energy, the total energy, which is equals to this kinetic energy and potential energy. Here's the 1 mv square and 1 kx, half kx square. So after simplifying that, mv square over 2, which is exactly equals to p square over 2m. How you can prove this term? When you divide the m in denominator and numerator, you will get m square v square over 2m. Okay, so m v whole square exactly equals to momentum value. So the p square you will put there. So for 3-dimensional, you can see for 1 dimension we have only 1 degree of freedom. For 3 dimension we have how many degree of freedom, you can see there. So this is for 3 terms kinetic energy, and this is the potential energy for the 3 terms. Now there are total 6 terms. Okay, and for per atom we have energy half kBT. Okay, so now you have to multiply and cancel the term. You will get these 3 kBT term for per atom for solid molecules. Okay, so further you can see these when we talk about for n number of atoms. Okay, in this case these you can put it down there n, and these are exactly equals to n into kb. Okay, this is the number of atoms, and this is the Boltzmann constant, which is exactly equals to the ideal gas constant. So you can put r instead of n, kb. Okay, now the specific heat is equals to rate of change in energy, which is equals to 3R. We have proved for a large number of molecules or for a single atom. For the expectation value of energy, the energy is obtained by differentiating the logarithm. Okay, so when we talk about the number of molecules, we exactly don't know about the energy, so we calculate probability. Okay, and probability can be calculated by taking averages of their values. So averages can be taken by the negative and differentiating the logarithm partition function term. Okay, this is the part z here, the partition function. So after taking logarithm, this is the value of some exponential term a, which is the expansion constant we shows. Okay, and this exactly equals to under root pi over, and this a, which is same this alpha. Okay, now this is the Hamiltonian operator you have studied already in quantum mechanics. So this is exactly equals to p square over 2m, which is also the operator, and half kx square. So this is the total energy. Hamiltonian shows this is the total energy of kinetic energy plus potential energy. So further you can see there's for the momentum p operator we use minus I h, which is constant, by taking differentiating with respect to their axis. So this is the operator. Okay, after applying operator we will get eigen function value. Okay, and this is the eigen's vector state. By applying the operator on vector state, we will get the eigenvalue term with eigenfunction or eigenstate, okay, vector state. Now by time independent Schrodinger, okay, equation, so of harmonic oscillator. So this is formula. Now we have to prove Einstein by using book, okay. This is the previous lecture. Here's some the numerical based expression, and you can write it down instead of theory. This is all about from this. So this energy is exactly equal to this h omega, which is the constant terms. This is the Planck's constant, and this is the Einstein frequency or oscillator frequency, and these ensures the number of terms and half, okay. So further you can see this is the summation notation. When we apply summation notation on some exponential with the negative Boltzmann with energy, and now you have to put the energy value instead of En. So En is the energy in some state, okay, and these state are already given, so you can put the values, and after solving, simplifying, arranging terms individually, you can see the n apply on one exponential. The second one is without n, okay. So without n term, you have to consider it as constant, so you have to put it outside of the summation, and the n with exponential term you will put inside the summation, okay. So further you can see, after putting these inside n term value, and this is the general formula when you have some n term. This is exactly equals to 1 over 1 minus r. So you can arrange this term in using this general formula. You can see we have only 1 over 1 minus e minus bh omega, and the remaining term are these we will use in next. Okay, so further we can see we are with this term. Actually, after putting this term in last equation, now you have to multiply e in the form of positive, okay, positive power, bh omega over 2 in numerator and denominator both. So you can see these minus term and these positive term will cancel. You are with only 1, okay. So after multiplying with 1 you will get the same term, and multiplying with this term you will get only 1, okay, same. And further we used the partition function, which is equal by hyperbolic formula, okay. And this term is exactly equals to sine h, okay, with some power value. Now the expectation of energy is with, okay, now we have to use the probability factor. We have to calculate energy. So the energy we already know, this is the formula for calculating energy. The negative of taking differentiating of log partition function. Now we already find out the partition function z value, which is 1 over 2 sine bh omega over 2, okay. Now first you have to change into law of logarithm by applying law of logarithm, and this quotient value will change into minus sign, and now further you have to apply log on individual terms. This term will get 0, and the next term you can see the log value, first it shifted 1 over log n term 1 over n, and then taking derivative of this term. So 1 over sine h and the value, and these we have to take the derivative of these terms. So the cos the sine which is equal to cos hyperbolic, and the inside value which is uh, equals to h omega over 2. We take these differentiating with respect to b, so we have to omit b there. So further, this is we are remaining with these terms. Okay, now further you can see that h omega and these terms actually we have to prove. How it comes? Let's go on. So using one. So here these expression we used to prove these last expression. So this is the law equation 1 value. Now you have to differentiate with respect to b again. Okay. So now differentiating numerator first, then denominator. So by differentiating numerator, we will get these terms. So you very well know that how to differentiate the term. So you will go on. Okay. And denominator, after taking the logarithm differentiating on denominator value, we are remaining with these terms. Now applying quotient rule on these terms. So quotient rule, this is the differential form of quotient rule, make sure. So first term, and then differentiating second term minus, and this then second term and differentiating first term with respect to second and divided by the denominator square value. So here we are with first we differentiate first term, second are same, then minus, and then we are with the first term same and taking differentiating of second term which is in the denominator. Already we have individually take the differentiating terms and then we put there in formula and divided by the whole term square. So this is the quotient rule. You can do it by your own self, then you make it clear very well. Okay, so you can see further after simplifying, multiply the term individually inside the term with inside the term, and after multiplying the terms and adding the power, you are remaining with these terms. So you can see these half bh omega when multiplied with these bh omega, you will you are remaining with the minus 3 over 2. Okay, and same the case with these terms. Now take the common values. There we are after taking common, we are with these terms 3 over 2, and when you individually rationalize it, we are with 1 plus 1 over 2. Okay, so here the one term is there, and 1 over 2 half term is on outside of this as common factor. So further you can see when we take these Planck's constant and oscillator frequency inside again. Okay, so we will get these equation exactly as the minus remains same. Now further you can see this is the formula actually in order to calculate the energy. Here the minus sign is also, you can put it down or not, actually it cancels in the last, it will cancel. Okay, okay, now you have to put the values. We calculated already the partition function value, which is equal to this the ratio form. Okay, and we already differentiating the term. This is the differentiating term. Okay, and now you can see this is the differentiating term. Okay, okay, and now you can see after simplifying, multiplying the terms and we will get these, we are remaining with this, and taking common we are remaining with this half, and we exactly have required to prove these terms. So here you can see that these minus factor, which should be ignored, because this is approximate very small value, and then for this we have to ignore it. Okay, so where the second term in the Bose-Einstein distribution, which gives the average number of boson. Okay, so the second term which gives the probability of number of bosons in the oscillation quantum state. So this is all about we have to prove. And further there is a graph. Okay, so in this graph we have studied that at low temperature, at high temperature, and at room temperature, how graph deviate. So you can see by yourself. This is the simplest derivation. Now you have to go with your own.